Welcome back to the AICE Chemistry Lecture Series. Today, in this video, we're going to focus on Chapter 4, Section 7, which is going to take a look at intermolecular forces. Now, a lot of these we discussed in honors chemistry, so some of these we're not going to discuss too in depth because you should have a lot of knowledge from last year. But we are going to look at the new vocabulary that we use to discuss intermolecular forces, as well as some new applications that we might have not seen last year. So let's get started. So Van der Waals forces are also called intermolecular forces. Now, as a general rule of thumb, we want to actually try to avoid using the term Van der Waals forces. So we want to avoid using this term because it actually means different things in different countries. If you were in AP chemistry right now, Van der Waals forces will be a synonym for London dispersion forces. In our curriculum, however, they're used as a replacement for the word intermolecular forces, and in some places they mean just London dispersion and dipole-dipole interactions, not hydrogen bonding. So we want to, just as a general rule of thumb, avoid using the term Van der Waals forces. We want to stick to the term intermolecular forces when we write out answers in the AICE exam. So intermolecular forces, what are they? They are forces of attraction that keep covalent molecules together. Now, what does this mean? Inter means between. So if we have a bunch of water molecules, for example, H2O, and I'm not going to draw the lone pairs because that's not the point of this, but if we have a bunch of water molecules, or any covalent molecule, this could be methane, this could be HCl, this could be NH3, doesn't really matter, but any kind of covalent molecule, intermolecular forces are not what holds hydrogen and oxygen together. Those are bonds. Intermolecular forces will be the forces that are connecting one molecule to another. Those forces of attraction keeping the molecules near each other are what we call intermolecular forces. Whereas the forces here, keeping the oxygen and the hydrogen together, are the bonds. So don't get the two confused. Bonds and intermolecular forces are distinct. Bonds keep the elements in a covalent molecule together, whereas intermolecular forces keep covalent molecules near each other or together near each other. The strength of many properties of covalent compounds can be explained through the strength of their intermolecular forces. So, for example, the boiling point, melting point of water being so high can be explained through the intermolecular forces that hold the molecules near each other. Because when a molecular compound or a covalent compound vaporizes or melts, what's separating is not the hydrogen and the oxygen, for example, in water, it's the molecules from each other. So the intermolecular forces are responsible for most physical properties of the molecules or of the compounds. We will discuss this in more detail further on, but before we discuss how these intermolecular forces are responsible for the physical properties of covalent compounds, let's discuss what these three intermolecular forces are. And there are three of them. In order of strength, increasing order of strength, meaning from weakest to strongest. The first of the intermolecular forces and the weakest is dipole forces, otherwise also known as instantaneous dipole-induced dipole forces, otherwise known as London dispersion forces. So these actually have three different names. I like to use London dispersion forces or dispersion forces. You can use whichever one you want. What I will tell you though is do not use acronyms. So when we're talking about instantaneous dipole-induced dipole forces or London dispersion forces, we should never write ID unless we have defined the first. ID, even though that is what your textbook uses and what I use here in the slides because of your textbook, is not an accepted substitute for the name of the London dispersion forces. So I would either use dispersion forces or London dispersion forces as the name, not instantaneous dipole induced dipole because that's very long, not IDID because we cannot use acronyms. Those are the weakest of the three forces, and we're going to look at how they come around in a few slides. Next is permanent dipole forces. What your book summarizes as PDPD, but again, we're not going to use that acronym. We're either going to say permanent dipole forces, or you could just shorten it to permanent dipole forces. You don't have to say it twice. Those are in the middle range. They're the middle of the three intermolecular forces in strength. And then the strongest of the three, which you have probably heard about many times in honors chemistry and in biology, is hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular force. And this is a bit to give you an idea of the strength of these. London dispersion forces are around 1 to 20 bond strength in kilojoules per mole. So kilojoules per mole is a measurement of energy per mole, which we'll discuss in chapter 6. But just to give you a numerical idea, permanent dipole forces are a little stronger than that, ranging from 5 to 20. So you can see how these two actually overlap, and we'll discuss that overlapping in a little bit. But these can actually overlap, and sometimes London dispersion forces are stronger than permanent dipole forces, and sometimes they're not. Hydrogen bonding, though, is definitely stronger than both of them, ranging from 20 to 50 kilojoules per mole. And then all of the intermolecular forces are all weaker than bonds. Covalent bonds are stronger than those intermolecular forces, jumping all the way up to 464 for the bonds in water specifically, although these bonds can range drastically in different molecules. And then ionic bonds jumping up to 760 for the one in sodium chloride specifically. So we can see how the bonds, ionic, covalent, even metallic, are way stronger than any of our intermolecular forces. Why can we lump them together? Well, in reality, these are all the same thing. They boil down to magnetic attractions, right? Whether it's covalent bonds of the attraction between the nuclei and the electrons, or ionic bonds, the attraction between cations and anions, or any of the intermolecular forces, which we'll discuss their various attractions. They're all just attractions between positives and negatives. The intermolecular forces are just much weaker attractions because they don't keep the elements in a molecule together. They just keep the molecules near each other. So let's delve a little deeper into some of the past topics that we are going to need in order to discuss intermolecular forces. And one of them being electronegativity. Electronegativity is key to understanding intermolecular forces, and it is something that we discussed in honors chemistry. It is the power of a particular atom that is covalently bonded to another atom to attract bonding pairs of electrons towards itself. So electronegativity is measured in the Pauling scale, which goes from 0.0 to 4.0, 4.0 being the highest in the scale, and it has no units. It increases across a period and decreases on a group, which we learned last year. So as we go from left to right, the electronegativity increases. You want to call it En. And as we go from up to down, so up top to bottom down a group, the electronegativity decreases. Now this is very important. Why? If we look at our periodic table for the AS exam, we have no electronegativity values in this table. The table gives us the element symbol, its atomic number, the name, and the atomic mass. It does not give us electronegativity values, and you're rarely going to be given electronegativity values in questions. So you should remember that the electronegativity, as we go from left to right, electronegativity is going to increase. And as we go from top to bottom down a group, the electronegativity is going to decrease. And I say this because all of the assumptions you will make about electronegativity are going to have to be made from this trend that you need to memorize. You will not be given the numbers. You need to start being comfortable with looking at two elements and start to estimate the size difference in the electronegativity. Now I'm going to give you a few tips when we talk about it in a second. I'm going to give you a few things you should remember, but you should always remember how electronegativity changes across a periodic table. Now, the same factors affect ionization energy also affect electronegativity. So why does the electronegativity of the elements, and let me bring back the other, our smaller version of this. Oh, it doesn't come all the go that far. But why does it increase across a period? Well, it increases across a period because nuclear charge of the atom or the elements increases as we go from left to right. The larger nuclear charge makes it more likely for atoms to attract electrons, meaning a higher electronegativity. On the other hand, why does the electronegativity decrease down a group? That's because of two factors, which are the same factors again that affect the ionization energy. Atomic radius gets smaller as we go up the group, or larger as we go down the group. The closer the nucleus is to the bonding electrons, the more it will attract them. The higher the electronegativity is as the atom is smaller. So what this means is that on the top of the group, where atoms are smaller, electronegativity is going to be bigger, whereas as we go down, because the size increases, electronegativity is going to decrease. And then shielding, and for the same reason, as we go down, we're adding layers to our atoms, and as we add layers, shielding also increases. And as shielding increases, that attraction for those electrons is going to decrease, decreasing electronegativity. So because as we go down the group, atomic radius increases and shielding increases, the electronegativity of the element is going to decrease. And because the nuclear charge increases as we go from left to right across a period, so does the electronegativity, because the attraction for those electrons is going to be larger. Now, how is the electronegativity though related to bonding? Because we are eventually going to connect this to talking about the intermolecular forces. So this has to relate somehow to the molecules themselves. Bonding and electronegativity is crucial in bonding because the difference in electronegativity values help us predict how a bond will behave and whether it will have polarity. If the electronegativity difference is too high between two elements, then the elements are going to just take electrons from each other. For example, lithium has an electronegativity of 1.0. Let me make that a different color. Whereas chlorine has an electronegativity of 3.0. Because of the difference is so large between chlorine and lithium, chlorine has a high electronegativity, meaning it wants to pull electrons towards itself. Whereas lithium has no way of fighting this. The difference is so large that the electrons actually transferred from lithium to chlorine, leading to the creation of lithium positive and chlorine negative, and therefore an ionic bond between the two. So if the difference is large, 2.0 or above, like here, then we are going to not have a sharing of electrons, we're going to have a transfer of electrons, meaning we're going to have an ionic bond. However, if the difference is low, like with carbon and nitrogen, where the difference is only 0.5, then we are more likely to have a covalent bond where electrons are shared. Think of this like a tug of war. If the two elements that are pulling on those electrons are pulling with relatively the same strength, those electrons are going to stay in between the two elements because these two elements are tying in the tug of war. But if the difference is too great, like with chlorine and lithium, one element wins the tug of war, in this case chlorine, and then the electron is transferred instead of shared. Now, this is a very honors chemistry view of things. These ranges are all shades of gray, and in reality, there isn't just a purely covalent or purely ionic bond in most cases. If the difference in electronegativity is somewhere in between 1.0 and 2.0, in compounds like aluminum chloride that we saw earlier, then the bond is not entirely covalent or entirely ionic. We get something in the middle. And that something in the middle is something like aluminum chloride or the acids, which we spoke about earlier in this chapter. All right, the aluminum chloride having both properties of covalent bonding and properties of ionic bonding. Now, if we look at our next slide, then we're going to get one of those shades of gray, which we call polar bonds. So covalent bonds, as we know, are bonds where electrons are shared between elements. Well, covalent bonds could have one of two versions. They could be what we call polar or non-polar covalent bonds. When atoms bond and they have similar electronegativities, the electrons are shared equally. When electrons are shared equally, we call that a non-polar bond. So when they have similar electronegativities, the electrons are shared equally. And that's what we call a non-polar bond. When atoms have very different electronegativities, however, and the electrons are shared unequally, so an equal sharing of electrons, we call that a polar bond. And what this leads to is an uneven charge on that bond. So when the electron pairs in the bond is drawn towards one atom, because that atom has a larger electronegtivity, making one end of the bond slightly positive and the other one slightly negative, that's what we call a polar bond. So if we have, for example, here hydrogen and chlorine, and we saw in the earlier slide that chlorine has an electronegativity of 3.0, hydrogen has an electronegativity of 2.0. So if we have a big discrepancy, like here we have 2.0 for hydrogen versus 3.0 for chlorine, that bond that's created, it's still a covalent bond because they're still being shared, the electrons. But the electrons are going to be more attracted towards chlorine, like this arrow is showing, than they are towards hydrogen. Essentially, chlorine is winning this tug of war, not to the point that it is completely taking the electrons, but the electrons are going to be closer to chlorine than they are to hydrogen in this bond. That creates a discrepancy in charge. Because chlorine has the electrons more of the time, it has what we call a partial negative charge. It's not a full negative charge, it's not an ion like Cl minus, but this side of the bond is going to have a partially negative charge. Whereas the hydrogen, which does not have the electrons as often or as much of the time, is going to form a partially positive charge. We use this lowercase delta, this Greek letter, to show a partial in chemistry. So this means partially positive, and this means partially negative. This is bond polarity. We call this bond polarity. The partial separation of charges when two different atoms are joined by a covalent bond, and happens when we have a polar covalent bond, where the electrons are pulled more towards one element than the other. We can also use this type of arrow, we call this a bond polarity arrow, which shows that the electrons are being pulled towards the chlorine. That's why it has the head of the arrow pointing towards chlorine. And then we have this positive sign made at the tail of the arrow on the hydrogen, which will be now partially positive. So this is just a review of polarity, which we learned in honors chemistry. Now, one of the things that you will need to realize that, again, you're not going to be given necessarily these electronegativities, so you will need to start being able to tell or to judge whether a bond is polar or not by simply looking at it. So I'm going to give you a few rule of thumbs here. First of all, a carbon-hydrogen bond is always nonpolar. You're never going to have a carbon-hydrogen bond that's polar. The electronegativities are too close to each other. And this is actually a very important nonpolar bond because we're going to see it a lot later on when we do organic chemistry. So try to commit to mind that a CH bond is nonpolar. Now, the other rule of thumb is that anything with nitrogen, oxygen, fluorine, or chlorine will be polar. Any bond that includes one of these elements will normally, most of the time, be a polar bond because these four are the strongest four or most electronegative four elements. Nitrogen, oxygen, and fluorine are the strongest, with fluorine being the first, oxygen being the second, and nitrogen being third. But chlorine has a special place in there because it also normally forms covalent bonds. So NOF or Cl, if you see them, it's going to be polar. So these are just two rules of thumb that you can use in most cases. The last thing, if it's not going to include one of these, which you usually will because there's not a lot of nonmetals to work with, is proximity. The closer two elements are, the more likely to be nonpolar. So closer means nonpolar. Farther away means usually polar. Obviously, this does not apply to hydrogen because hydrogen is in a weird space in the periodic table, but it does apply to things like phosphorus and sulfur, for example, which are right next to each other. And so phosphorus-sulfur bond is likely to be nonpolar, where a carbon-iodine bond is likely to be polar because the elements are so far away from each other. Or a phosphorus-iodine bond is likely to be polar because their elements are so far away from each other. So this is just a few rule of thumbs that you can think of when you're trying to gauge if a bond has polarity or not. All right? You will have to kind of play by ear. A lot of the time, the question itself will have a lot of context clues that can tell you whether a molecule is polar or not. But in general, you can use those rules of thumb to give yourself an idea. All right, moving on. So this is for bond polarity. Now, bond polarity is different than molecular polarity. A bond could be polar in a molecule, but it might not mean that the molecule itself will be polar. We have plenty of examples of molecules where the bonds in the molecule are polar, but the molecule becomes nonpolar. And that's because molecular polarity is also tied to shape. The polarity of a molecule depends on two factors. The polarity of the bonds is one of them, because you cannot really have a polar molecule without polar bonds. But the arrangement of the bonds in that molecule is another factor. Essentially, the shape of the molecule and where the bonds are located. This is particularly important to understand because once we do organic chemistry and we're looking at much larger molecules, we start to discuss whether areas of the molecule are polar versus the whole molecule. So a molecule is going to be polar if it has polar bonds that do not cancel themselves out. And this is where being able to visualize three-dimensional molecules comes in. Polar bonds are going to cancel each other out if the direction of the bonds point in opposite directions or different directions without any general agreement. We basically saying that if the bonds are symmetrical, then we're going to cancel them out or cancel the polarity out. If the bonds, on the other hand, are not symmetrical, they're asymmetrical, and they don't agree in a general, or they agree in a general direction of the negative and the positives, then the molecule will be polar. So here we have three examples. For CH4, we have a nonpolar molecule. Why? We discussed how the carbon-hydrogen bond is nonpolar. So because all of the bonds in CH4 are nonpolar, CH4 is a nonpolar molecule. On the other hand, here in the middle, we have a situation where we have polar bonds and polar molecules. If we look at CHCl3 here, and we look at this tetrahedral shape that we have for this molecule, if we look at the chlorine bonds, carbon-chlorine bonds, those are going to be polar because, again, anything with chlorine is generally polar. The carbon-hydrogen bond, on the other hand, is nonpolar. There is a net agreement of the direction of the polarity. All of the carbon-chlorine bonds have the polarity of that bond pointing towards the bottom of the molecule. You need to be able to visualize this in 3 dimensions as a tripod to do this, and not just as a cross or as a flat drawing. If we visualize this as a tripod, we can see how the bonds that are polar, the carbon-chlorine bonds, all have the negative charge on the bond pointing towards the bottom. The carbon-chlorine bond has the chlorines being partially negative because they're the more electronegative element, with the carbon being partially positive. If all of the chlorines are partially negative and they stand at the bottom of our tetrahedral, at the feet of the tripod, we can say that overall the bottom of the molecule is partially negative and the top of the molecule is partially positive. And so we can draw a dipole arrow that points down on this molecule because that's where the general negative charge is, with the general positive charge being on the top. So this is an example of a molecule with both polar and non-polar bonds that is asymmetrical because all of the chlorines are at the bottom or at one side, meaning that the bond itself will be polar. Now, the last one here is an example of a molecule that is symmetrical. So CCl4 is a molecule that has all polar bonds. There are no non-polar bonds in CCl4. However, even though there are all polar bonds in the molecule as a whole is actually non-polar. Why? Because all of the bonds that are polar cancel each other out. If we look at the carbon-chlorine bond, again, it's polar because chlorines usually means that we have a polar molecule. And the chlorines are the partially negative charges, whereas the carbon has a partial positive charge. Because the carbon is the least electronegative element. Well, if we again visualize this as a tripod, as a tetrahedral, we can see that there's no net agreement in the direction of the negative bond, or the negative pole of the bonds. There is negative at the top, negative at the bottom, negatives on the right, negatives on the left. This molecule is symmetrical. We have 4 identical bonds that are all polar, but they all point in different directions. So because the molecule is symmetrical, the bond and the bonds are polar, this overall molecule is non-polar because the bonds end up canceling each other out. And that's just a review of polarity, both bond polarity and molecular polarity, which are different topics for AS chemistry. But again, this is all mostly a review from honors chemistry. Now let's look at this. Explain why ammonia molecule is polar. So in order to explain why the ammonia molecule is polar, we need to be able to draw the ammonia molecule. You might not have fully understood this yet, although you will as time goes on, but ammonia is NH3. So let's look at our ammonia molecule, NH3. Nitrogen has 5 lone pairs of valence electrons, because it's in group 15. Whereas hydrogen is in group 1 and therefore has 1 valence electron. So ammonia, if we create our bonds, and there is no need here for any expanded octets, and nitrogen can expand its octet anyway because it's not in period 3. If we draw our molecule, we end up with N, H, H, H. Now, our problem here is that this is a 2-dimensional Lewis structure. When we're talking about polarity, we want to draw our structure in 3 dimensions. Ammonia is a trigonal pyramid or a pyramid-shaped molecule. So we're going to have a hydrogen sticking out towards us, a hydrogen on the paper, and then a hydrogen that goes back away from us with a lone pair of electrons at the top of the molecule. Like we said earlier, anything with anything with nitrogen is going to be polar. So all three of these bonds are polar. And because nitrogen is the third most electronegative element, the nitrogen is partially negative, with the hydrogens being partially positive. And again, this is where being able to visualize in 3 dimensions comes in. Because the nitrogen is at the top, and this stands like a pyramid with the hydrogens at the bottom, we have a net polarity to the molecule. Because the bottom of the molecule, the hydrogens are partially positive, I drew this arrow backwards, are partially positive, whereas the nitrogen is partially negative, which is at the top. So we can draw a polarity arrow that points up because it's pointing towards the negative side of the molecule, the top, the nitrogen, with the positive side being at the bottom, being the hydrogens. So why is ammonia polar? They had told us it's polar. The question is why? Well, it's an asymmetrical molecule. It's an asymmetrical molecule. I don't know why that's that. So it's an asymmetrical molecule because the polarity, even though all the bonds are polar, they do agree on a general direction. There's a net positive charge in the bottom of the molecule and a net negative charge at the top. And it has polar bonds. So let's look back at the question. If we look at the ammonia molecule, why is it polar? Again, it's asymmetrical and it has polar bonds, meaning that what do the bonds not do? The bonds do not cancel out. The only way you're going to have a molecule with polar bonds that is not polar is if you had a symmetrical molecule. And I see here the spaces might be a little confusing. If you have a symmetrical molecule that the polar bonds cancel out, that will be a non-polar molecule. But because ammonia is asymmetrical, does not have symmetry, and the bonds are polar, the bonds do not cancel out, and therefore we have a polar molecule. So if we look at the answer for this question, the mark scheme, you will see that the mark scheme requires us to say that the molecule is not symmetrical or that the dipoles do not cancel out. Which the dipoles not canceling out is caused by the fact that the molecule is not symmetrical. So, now that we looked at what a question about this could look like on the AICE exam, let's look at our how we use polarity. Because being able to tell whether a molecule is symmetrical or not, or polar or not, being able to tell whether the bonds are polar or not, are tools that we use to discuss other topics in chemistry. They're a basic understanding. That's why we study polarity in honors chemistry. We study in honors chemistry how to tell if a molecule was polar, if a bond was polar, so that now in AS we can talk about different things based on polarity. Now, one of the things that polarity affects is the chemical reactivity of a molecule. So the simple fact is that when a molecule has polar parts to it, or when a molecule itself is polar, it will attract more compounds. That partial positive, that partial negative in a polar molecule or a polar bond will call or attract other molecules to come and essentially interact with that molecule, creating chemical reactivity, creating chemical reactions. When bonds are non-polar, then they're non-reactive. When a molecule is non-polar, it's non-reactive. So molecules like N2, nitrogen gas, which has two nitrogens with a triple bond, no polarity, because both the nitrogens have the same electronegativity. Or when we have something like C2H6, ethane, which has all carbon-hydrogen bonds, which are all nonpolar, and therefore has no polarity, those molecules are said to be unreactive or non-reactive, because the lack of partial positives and negatives are going to mean that other molecules will leave these molecules alone. They're not attracted to them. Again, everything in chemistry can boil down to magnetism. The more magnetism there is, the more things will happen, and the more reactions you'll have. So things that are nonpolar and are therefore very unlikely to suffer from magnetism and magnetic attraction are not going to be very reactive. On the other hand, if we have a molecule as a whole that's polar, like carbon monoxide, where the difference between carbon and oxygen, which is the second most electronegative element, is great, we can have a polar molecule and a polar bond. That partial negative is going to attract all sorts of this partial negative is going to attract all sorts of positive things, and this partial positive will attract all forms of negative things. And those other molecules that have the partial positives or partial negative charges, or full positive and full negative charges, are going to interact with this carbon monoxide. Same thing here. If we replace one of the hydrogens in ethane and we replace it with a chlorine, we get chloroethane. Chloroethane is reactive, unlike ethane, which is non-reactive. Why? By adding that chlorine, we have now added a polar bond to the molecule. Polar bonds, like I said, are going to attract things. That partial positive on the carbon will attract things with a negative charge. That partial negative on chlorine will attract things with a positive charge. And so this molecule becomes reactive, especially along this bond. A lot of the reactions that happened with chloroethane happened to the carbon-chlorine bond. And those reactions will change the carbon-chlorine bond because of its polarity. So look at another question here. Let's look at this question. Hydrogen cyanide, HCN, is a gas which also is isoelectronic with N2 and CO. Each molecule contains a strong triple bond with the following bond energies. So they're telling us a few things here. They're telling us that these molecules are isoelectronic. Remember, isoelectronic means same electron configuration, and when we're talking about a whole molecule, means same number of electrons. And then it tells each molecule contains a strong triple bond. So all of them have a triple bond with the following bond energies. So they give us bond energy, bond energy, bond energy. So here's the triple bonds. And then it tells, although each compound contains the same number of electrons and a strong triple bond in the molecule, CO and HCN are both very reactive, whereas N2 is not. Suggest a reason. So what they're telling us here, the way this question is structured, is that they're telling us what's the same. They're telling us they both have triple bonds. They're telling us they're all isoelectronic, so they have the same number of electrons. But they're telling us, explain the thing that is different. Explain why CO and HCN are reactive, whereas N2 is not. So then what this question is guiding us to do is to start thinking about things that are different. So what is different between these three molecules? So let's draw them out. We have N2, which should be fairly simple to draw out. Nitrogen needs to form 3 bonds. So it's on a triple bond to itself. Then we have carbon monoxide, which we also had just seen. And this is a molecule that you should probably memorize because it is a very common molecule that comes up on the test, but one that is hard to actually come up with a Lewis structure for. We have carbon monoxide, which is also triple bonded, as they told us, and they're actually showing us a molecule here. And then we have HCN. Nitrogen forms 3 bonds, and so it can form 3 bonds to carbon. And let me center this a little better. So we can put carbon in the middle. And the carbon is going to form 3 bonds to the nitrogen because nitrogen forms 3 bonds. Carbon forms 4 bonds because of their group numbers. And they're showing us right here that carbon is triple bonded to nitrogen. And then single bonded to hydrogen because that carbon does need 4 bonds to achieve the octet. Well, if we look at these 3 molecules and we start to understand what's different, Obviously, they all have triple bonds. That's not the difference. We could look at the fact that there's a hydrogen on the carbon in HCN, but that wouldn't really give us much of a difference there. Or we could start looking at their polarity. Nitrogen is not going to be polar because it has two of the same element. The carbon-oxygen bond, on the other hand, though, is polar, with carbon being partially positive and oxygen being partially negative. Because, like I said before, one of the rules of thumb we can look at is that anything with oxygen is really going to be polar. Now, obviously, I mean oxygen bonded to something else, because if it's bonded to itself, it's going to be nonpolar. But here, with this carbon-oxygen bond, is polar. Also, in HCN, the carbon-nitrogen bond is going to be polar because, again, anything with nitrogen is usually polar. N2 is non-polar because it's bonded to itself. But here we have carbon and nitrogen bonded to each other. That's a polar molecule, or a polar bond at least. And it's also a polar molecule because it's asymmetrical. The carbon-hydrogen bond is non-polar, meaning that there is a partial positive side to a molecule and a partial negative side to a molecule. So if we look at it here, it says, suggest the reason for this. It suggests the reason why carbon monoxide and HCN are both reactive, but N2 is not. So it's an N2 versus CO and HCN fight. And we can easily see here how HCN and CO share the trait of being polar, whereas N2 is nonpolar. So the most likely answer here, the answer we had just finished going over, is the fact that carbon monoxide and HCN both have a dipole, or they're polar, or that N2 does not have a dipole. And realistically speaking, you should mention both. This is a comparison question. So you should say that CO and HCN are polar or have a dipole, whilst N2 is non-polar or does not have a dipole. And that should be a very valid answer. So this is one of the ways in which we can use polarity to explain the properties of molecules. In this particular case, the reactivity of molecules. Next, we're going to see how the polarity can help us explain the other type of property. Because here we're talking about reactivity. We are talking about a chemical property. How likely are they to react? But let's see how the polarity can also help us talk about physical properties when we talk about intermolecular forces. Now, again, I'm going to very briefly go over each intermolecular force because we did cover them in honors chemistry, but a refresher is good. So we're going to start with the weakest of the three forces, instantaneous dipole, induced dipole, or what I prefer to call London dispersion forces. I'm going to put that name up here in the top. You can call them either or, but do not use IDID unless you have previously said instantaneous dipole, induced dipole, and then IDID in parentheses. Then you can use IDID over and over again. Or you can just call them London dispersion forces, or simply just dispersion forces for short, if you want to use a shorter name. Again, do not use the term van der Waals forces because that can be very confusing depending on where you're from. So the intermolecular forces, which we call London dispersion forces, are forces of attraction that are the weakest. Why are they the weakest? How do London dispersion forces occur? Simply put, they occur by chance and the random movement of electrons. If we have an atom, atoms are usually pretty well evenly divided. They have electrons in them. So this atom is going to have its electrons inside. And it has a bunch of electrons just floating around. Well, these electrons are always moving around. They're constantly in motion. Because of random chance, a bunch of these electrons might end up, and let me use a different color, a lot of these electrons might end up on one side of the molecule. So if by random chance, because of the random movement, a lot of electrons end up in one side of the molecule, what that creates is what we call a temporary dipole, or an instantaneous dipole if we look at the name. What is an instantaneous dipole? It is a dipole, a partial negative and a partial positive side to this molecule that occurs by random chance. They have very short lifespans. They just exist for a few milliseconds. But for those few milliseconds, because a lot of electrons are on one side of the molecule, that molecule is going to be partially negative on one side and then partially positive on the other. Well, if a molecule with a temporary dipole gets really close to a molecule without one where the electrons are very evenly distributed, something is going to happen. The partial negative side of one molecule, the temporary dipole molecule, is going to repel the electrons and push them to the other side of a molecule near it. So essentially, if we have these two molecules near each other, the partial negative side, the partial positive side, this partial positive side could attract the electrons on this molecule, shoving all of the electrons in this molecule to that side. Well, if suddenly this molecule now has a bunch of electrons on one side, that side becomes partially negative, and the other side becomes partially positive. This is what we call an induced dipole. That's why this is called instantaneous dipole, induced dipole. A dipole that was created, or a partial positive, partial negative side on a molecule that is normally not polar, was created because of the random movement of electrons. That's the instantaneous dipole or temporary dipole. And then it induces a dipole on a neighboring molecule. So the partial positive, you can see here, the partial positive side of this molecule is attracting the electrons in this molecule, creating a partial negative side and a partial positive side on this molecule. Well, because that partial negative ends up next to a partial positive here, these two are going to attract each other. That attraction of an induced dipole for a temporary dipole, or vice versa, is called the London dispersion force. Now, why are these forces weak? They only exist for a few milliseconds, and they're due to random chance. So they have very short lifespans. And so, because they have very short lifespans, they are not very strong. This is why these are the weakest of the intermolecular forces. But because they do exist, and because they do have some form of strength, they are still important. All right? Now, these forces happen in every molecule. Whether a molecule is polar or non-polar, they will happen in every molecule. So, induced dipole, today's dipole, induced dipole forces, or London dispersion forces happen in all molecules, regardless of whether they're polar or non-polar. Last year in honors chemistry, we said they only happen in non-polar molecules. And realistically speaking, what we're saying is that they are most important for non-polar molecules because they're the only intermolecular force in non-polar molecules. But now that we are looking at a deeper level of understanding in chemistry, all molecules will have instantaneous dipole and induced dipole forces. Because sometimes these can be important even in polar molecules, and we'll see why. But before we look at why and we start comparing these two polar molecules, let's talk about what can make these London dispersion forces either weaker or stronger. So there are two factors that are going to affect the strength of the London dispersion forces. London dispersion forces, or instantaneous dipole, induced dipole forces, are going to get stronger, first of all, with increasing number of electrons. And that makes sense, right? Because if we have more electrons, then it's more likely that an instantaneous dipole will form, a temporary dipole will form. The larger number of electrons will also lead to a larger number of London dispersion forces. We can see this in the boiling point of the noble gases. Why boiling point? The boiling point of noble gas and the boiling point of most molecules is going to be affected by their intermolecular forces. In the case of the noble gases, because the noble gases are nonpolar, the London dispersion forces are the only intermolecular force that these gases have. So we can look at the boiling point of the noble gases as a direct indication of the strength of their London dispersion forces. So we can see here that as we go from helium to neon to argon to krypton to xenon, the boiling point goes up. Why is this the case? As we go from helium to neon to argon to krypton to xenon, what we're doing is we're going down the group. So we have helium, neon, argon, krypton, and helium. Oh, sorry, and xenon. If we look at the periodic table and we look at the neutral atoms of these gases, we can see that helium has 2 electrons, neon has 10 electrons, argon has 18 electrons, because remember, they're neutral, the number of protons is equal to the number of electrons. Krypton has 36 and xenon has 54. So as we go down, not only do the sizes increase, the number of electrons increases. As the number of electrons increases, so does the strength of the London dispersion forces. So, as the size goes up, the number of electrons increases. As the number of electrons increases, the London dispersion forces, or LDF, get stronger. So the forces that are, if I have a bunch of atoms of a noble gas, the forces that are attracting all of these atoms of the noble gases together are increasing as we go down the group. And if these are increasing, if they're getting stronger, that means it's going to take more energy to separate those atoms and turn them into gases. That's why as the number of electrons increases, as the London dispersion forces get stronger because of that increased number of electrons, the boiling point of the noble gases increases as well. All right? Don't worry about why it's not linear. That's not the point here. We need to worry about the fact that it's increasing. So when we're comparing the boiling point or melting point or any physical property of a molecule that is usually nonpolar, although we could include polar molecules in this, the more electrons a molecule has, the stronger the intermolecular forces, specifically the London dispersion forces are, and so the higher the boiling point, melting point, so on and so forth will be. So LDF gets stronger, meaning boiling point, let me use a different color, meaning that the boiling point or the melting point will increase as well as we go down. Now, that's when we're comparing molecules with different number of electrons. What if we're comparing two molecules that have the same number of electrons, but their boiling points and melting points are still different? That's going to bring us to this right side of the slide here, which talks about contact points. What are contact points? Contact points refers to how flat a molecule is. So that's a much easier way of thinking about it. We call them contact points, but how flat is this molecule? The flatter molecules, the more contact points. You can think of it as surface area. The more surface area a molecule has, the stronger the London dispersion forces will be. Why? What makes a flatter molecule have stronger London dispersion forces? The answer is the number of places where these London dispersion forces can happen. Let's take, for example, these two molecules, pentane and 2,2-dimethylpropane. And I know that's a mouthful. So we have pentane here with a boiling point of 36 degrees Celsius. And then on the other side, we have 2,2-dimethylpropane, and you'll learn where the name comes from with organic chemistry, with a boiling point of 10 degrees Celsius. So even though these molecules are very similar, and what do I mean by very similar? If we look here, pentane has 1, 2, 3, 4, 5 carbons. Oops, let me make that smaller. Pentane has 5 carbons, and they have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. Then if we look at 2,2-dimethylpropane here, we have 1, 2, 3, 4, 5 carbons. And then we have 3, 6, 9, 12 hydrogens. So both 2,2-dimethylpropane and pentane have the exact same chemical formula. They're what we call isotopes, and we'll discuss what isotopes are in chapter 14. But they have the exact same chemical formula, meaning they have the same number of electrons. So both pentane and 2,2-dimethylpropane have the exact same chemical formula and the exact same number of electrons. However, pentane has a higher boiling point than the 2,2-dimethylpropane does. Why? The answer is their shape. This is what pentane looks like. It's a flat molecule where the carbons are bonded in a line with their hydrogens attached to them. And this is what 2,2-dimethylpropane looks like. You have a carbon in the middle with 4 carbons attached to it, and each of those carbons has 3 hydrogens attached to it. Pentane is a much flatter molecule. It is long, it is linear, whereas 2,2-dimethylpropane is a much rounder molecule. It has a central atom with atoms around it, and so when two 2,2-dimethylpropane molecules come together, they have very few places where London dispersion forces can happen. Essentially, they can only happen between these edges of the molecule. So the contact points, the number of contact points, is a lot smaller because 2,2-dimethylpropane is not flat. On the other hand, since pentane is flat, there's a lot more places where these contact points can be. There's a lot more places where London dispersion forces can happen, and so they attract each other a lot more strongly. Essentially, the London dispersion forces are stronger with pentane than they are with 2,2-dimethylpropane. So this is weaker London dispersion forces, because the number of contact points is smaller because it's not as flat of a molecule. We can see that in their boiling point. Pentane has a boiling point of 36, whereas 2,2-dimethylpropane has a boiling point of 10. And why is this one so much higher? Because it has more contact points, therefore stronger London dispersion forces. So that is the second property that will affect the strength of the London dispersion forces, and therefore the physical properties of the molecules, like boiling point and melting point. The number of electrons and the number of contact points. Generally speaking, we use them for different things. We'll talk about the number of contact points or how flat a molecule is when we're comparing two molecules that are very similar. For example, two molecules have the exact same chemical formulas and therefore the same number of electrons. Whereas when we have molecules or elements, in the case of the noble gases, that have different number of electrons, we will compare them based on the different number of electrons and how that affects the London dispersion forces. We rarely ever talk about both of these at the same time. You have to focus when you're answering questions on one or the other. Are we going to answer the question based on contact points, because the molecules are very similar and have the same number of electrons or similar number of electrons? Or are we going to answer based on the number of electrons because the things that you're comparing have very different number of electrons? Now, the second type of intermolecular force, and the one that is much easier to discuss, is permanent dipole forces, or what we call dipole forces in honors chemistry. These are easier to discuss because they do not happen in every molecule. Permanent dipole forces only occur in polar molecules. So they're only ever going to happen in if a molecule is polar. Why? Permanent dipole forces, as the name implies, only happens when there is a permanent dipole, meaning we have a polar molecule. These type of forces are essentially going to be very straightforward. It is the partial negative side of a molecule, or the partial negative side or atom of a molecule, attracting the partial positive side of different or even the same type of molecule. So for example, if we have something like formaldehyde, COOCH3CH3, the carbon-oxygen bond here is polar, with the oxygen being partially negative and the carbon being partially positive. Because that oxygen is partially negative, it can attract the partial positive carbon of a different molecule. Because positive and negatives attract. That's a fact of nature, right? It's a fact of life, fact of physics and magnetism. So the partial positive, partial negative attract each other, and they form what we call the permanent dipole force. It is a weak force, but it is usually stronger than London dispersion forces. While polar molecules also have London dispersion forces, usually the dipole force is more prominent and stronger. It overshadows it. However, some very large polar molecule, or sorry, very large polar molecules can also have the London dispersion forces affect them. Sometimes when a molecule is large enough, the London dispersion forces can overshadow the permanent dipole forces. So let's look at a couple of questions, one from paper 1 and one from paper 2, that are going to ask us to use this knowledge to figure out the difference between certain molecules. So we're going to start with a paper 1 question. The boiling point of Br2, ICL, and IBr are given in the table below. So they give us 3 molecules that we're going to compare, and they give us their boiling points. But be very careful, because these type of questions are not asking you to compare all 3 molecules to each other. As you can see here, we have a chart type multiple choice question where we have essentially 2 columns of a chart and the rows represent our answer choices. What they're asking us to explain is why the boiling point of ICL is greater than that of Br2, and then why is the boiling point of IBr greater than that of ICL. So we're not comparing all of these molecules, we are comparing them in pairs. So we're comparing Br2 to ICL, and then we're comparing ICL to IBr. So in order to answer any of these questions, we really need to think about the structure of the molecule. Br2 is easy because we have 2 bromines single bonded to each other. So we have Br. I'm not going to draw the lone pairs of electrons because they're not important here, right? So that's something that you need to start getting used to in order to save time on the test. Don't try to be a perfectionist when you're trying to do sketches to figure out something. Just write what is important. ICL, we have an iodine single bonded to a chlorine. Both of these are group 17 elements, so we know they only make 1 bond normally. So this is the logical molecule, a single bond between the 2 of them. And then same thing with IBr. 1 bond between the iodine and the bromine because they're both group 17 elements. When we think of this, because they're asking us to compare the boiling points, we should now be aware that we should be looking at polarity. Br molecules are going to be nonpolar because they have 2 of the same element. ICL, like I said earlier, is likely to be polar because it has chlorine, and IBr is also likely to be polar because it's 2 different molecules and they're both halogens. Halogens in general are pretty much going to make guaranteed polar molecules most of the time. Now, when we're comparing Br2 to ICL in this first part, and we'll do this in blue, or actually in pink. In this first part, when we're comparing a Br2 to ICL, we're comparing a non-polar molecule to a polar molecule. So this should be a pretty easy, straightforward thing. Why? Non-polar molecules only have 1 type of intermolecular force, which is London dispersion forces. Whereas polar molecules like ICL have both London dispersion forces and permanent dipole forces. So we'll just put PD here. So what is the difference between Br2 and ICL? ICL has permanent dipole forces, whereas Br2 does not. That alone should actually allow us to narrow down our answer choices to 2 of them. So if we look at A, boiling point of ICL is greater than that of Br2 because ICL has stronger instantaneous dipole-induced dipole forces. That might be true. We will have to count the number of electrons. ICL has permanent dipole forces. That's definitely true. ICL has stronger instantaneous dipole-induced dipole forces. Again, could be true, we have to count the number of electrons. And ICL has permanent dipoles. Well, this could be true, but B and D are definitely true. So chances are the answer is not going to be C. The answer is not going to be A. If we counted the number of electrons, we'll actually realize that they're around the same. They are slightly higher, but they're around the same. So the better answer, because there is a lot of the time a better answer, not just a right answer, is that ICL has permanent dipole forces. Now, that leaves us with two answer choices. And if we didn't know how to answer the second part of this, we could very much guess and have a 50-50 chance. But if we go and look at ICL and IBR, IBR being polar also has London dispersion forces and PD or permanent dipole forces. So what is different between these two? Here is what I was talking about earlier. We cannot necessarily here talk about the polarity. Why? Both of these molecules are polar. We are never going to be asked to compare how polar a molecule is. So they're not going to ask us to compare if IBR is more polar than ICL or vice versa. When you get into the situation where both the molecules you're comparing for the second question have polar permanent dipole forces, what you're actually going to end up comparing is the London dispersion forces. Why? IBR has more electrons than ICL. If we think about it, the halogens go fluorine, chlorine, bromine, and iodine. So in IBR, we have the two heaviest halogens, where in ICL, we have the heaviest and the second heaviest. Meaning that because the number of electrons increases as we go down, IBR is going to have more electrons than ICL. And therefore, it's going to have stronger London dispersion forces. And so if we look here, IBR has strong instantaneous induced dipole forces versus D, which says IBR has stronger permanent dipole forces. Without having electronegativity numbers, we have no way of knowing if this is true. Meaning the answer cannot be D, and therefore has to be B. Again, is this possible? Yeah, it could be. We don't know because we're not given the electronegativity of those elements. We're never going to compare permanent dipoles, so we're never going to compare how polar a molecule is. So the answer has to be B here. And we can see that the answer is indeed B for those reasons. So when comparing two things, it just goes to show you, when comparing two things that have different intermolecular forces, like Br2, which has just London dispersion, and ICL, which has both London dispersion and permanent dipole, we focus on that difference. But when comparing two things that have the same intermolecular forces, London dispersion forces and permanent dipole, like it is in the case with ICL and IBR, then we're going to focus on the one we can actually compare, which is London dispersion forces, which we can compare both in sense of number of electrons or how flat a molecule is. We're never going to compare how polar a molecule is, or a permanent dipole force and how strong they are. Let's look at now at a question from paper 2. This question follows similar points. Hydrogen iodide, HI, is a colorless gas at room temperature. Okay, we didn't need to know that necessarily. Explain why HI has a higher boiling point than HCl and HBr. So again, here we're looking at halogens, and they do like to use the halogens a lot in these questions because we should be very familiar with them. So here we're comparing HI, HBr, and HCl. And again, we can instantly see here that the polarity is going to be very much the same because all of these are polar molecules, meaning they all have permanent dipole forces. So are we realistically going to compare their polarity? No, because we don't have any electronegativity numbers. Instead, what we have to compare is the other force that they all share, which is the London dispersion forces. Now, because the hydrogens are all the same, we can actually compare the halogens. We have iodine, negative. We have bromine, and we have chlorine. if we think of them in the periodic table is fluorine, chlorine, well, bromine, then iodine, with the number of electrons increasing as we go down. Meaning HI has more electrons than chlorine, which has less electrons. So what do you think the explanation is going to be here for why HI has a higher boiling point? Well, since HI has more electrons, it has stronger London dispersion forces. And that's what we need to mention. Now, we need to mention both of these things. So notice, this question is 2 points. So we look here, this is a 2-point question. Meaning when we look at the answer now, you'll see that there are 2 points to this answer. The first is that the iodine, the HI, has a greater number of electrons. You could say iodine or HI has a greater number of electrons, which causes the greater induced dipoles or London dispersion forces between molecules. And that's why it has a higher boiling point. If this was a 1-point question, we would probably just get away with saying it has a great number of electrons, but especially because it's a 2-point question, and you should always do it just in case, we need to state both that it has a great number of electrons and this causes a greater or stronger induced dipole or London dispersion force. All right, so you gotta be very careful that you have a clear idea. It's very useful a lot of the time to draw these kind of diagrams on the sides of your questions so you can have a clear idea of what you're addressing when you're answering the question and not lose track and essentially write everything you know about the topic. So very clear here with a little diagram. HI has more electrons than HCl, which causes the London dispersion forces to be stronger. So what would my answer be? HI has more electrons than HBr or HCl, which causes its London dispersion forces or greater induced dipole forces to be greater. Very straightforward, very to the point, and we're focusing just on what is different between these, not the permanent dipole, which is going to be the same for all of them because they're all polar molecules. All right, so that is it for section 7 of chapter 4. I'll see you all in the next video.